3.26 should bring back memories of things we did at the very beginning of the semester, although I will quickly admit it's been a long, long time since the beginning of the semester. But we did this activity in class where we had a piece of paper, and the piece of paper looked like this, and we cut squares out. So I gave each of you a piece of paper, and you each cut a square out. And then what we did was we took that piece of paper and we folded it, and then once we folded it, we created a box. And so hopefully you can kind of see that box there. Okay, so we folded it and then we said, what's the volume? And so you notice that box has a length and a width and a height. So the question is, what's the largest we can make the volume of that box? Well, if we're going to do this, we need to follow our basic principle. And our basic principles are to draw a moving picture of our problem, label it with some variables, create an equation, substitute until we get only one variable, and then find a max or a min. It turns out we won't have to do number 4 because it's going to be pretty obvious what that substitution is. I think. Actually, maybe not. Maybe it won't be obvious. It depends on how we think about the problem. Okay, so let's come here. And first, our picture is going to be pretty simple. We just cut out the boxes. So here, I'll just pretend that this whiteboard is my piece of paper, and I cut them all out. And now I need to label. And what you'll notice I need to label is I have an X here, and these are all squares. So these are all the same sizes each time. And then I should probably label like these distances here that I'm going to fold along. So if I look, this is that base that I'm folding, and so these are each of the bases. So why don't I call this just like X, and maybe I can call this the length and the width. And what you notice is that our X is our height. So I'm going to kind of think of this as my picture. And now let's come and let's try to think about how do I solve this problem. Well, I need an equation to work with, and my equation is that let me move my little image here out, and I need an equation to work with. And my equation is that the volume, well, we know volume is length times width times height, but in this case height is just going to be X, because if you think about our picture, when we fold it up, this length is going to be how tall it is. Okay, so we get length times width times X, but now I can do a few more things because I know that this length right here, well, I noticed that the length of my entire paper was 11, so this is 11 minus, but I had to cut off an X, and I had to cut off another X, so it's 11 minus 2X is that right here. So I know that my volume is 11 minus 2X, so I've now substituted to get rid of one variable. And then I know my width, well, this side was 8.5 minus 2X, because I had to subtract an X here and subtract an X here. So then that becomes 8.5 minus 2X times X. All right, so this looks like my equation, and now I need to do some calculus on this. I have a choice. I can either do a few product rules here when I do my calculus to find where this is a max or a min. But by the way, let's come and verify. I've drawn my picture, I labeled, so I put my X, L, and W. I created my equation, and I substituted. So now I'm on step 5, where I find the max and min using calculus. So I just want to take the derivative of this and set it equal to 0. Again, I could use a bunch of product rules. I'm going to do a little bit of algebra first, so I'm going to FOIL this out, and because I think that'll make life easier for me in just a second. So my volume, let's see, I need 8.5 times 11. Oh, what is that? Let's see. It's halfway between 88 and 99. So that's 88 plus 5.5 is 93.5. Did I get that right? I'm going to check because I'm not confident. Oh, good, I got it. Okay, 93.5 minus, then I get 2 times 8.5, which is 17x, and 2 times 11, 22x. Oh. And then I've got 2 times 2, which is plus 4x squared, all times that last x there, and I'm running out of space. Sorry, folks. I'm doing my best. Let's write it down one more time, and let's combine the things. So this is my constant, So this is 93.5x. I'm going to go ahead and distribute my x in. 17 and 22 becomes 29, 39 x squared plus 4 x cubed. You notice this x that you can barely see here on the edge, I went ahead and distributed it into everything, and I added those two together. Okay, I've just done a little bit of algebra. I've got this. Now I'm ready to do my calculus. My calculus means I need to take the derivative of this. This derivative is pretty simple. It's 93.5 minus, and 39 times 2 is 78x, and then 4x cubed times 4 is 12x squared. So I need to figure out where this thing is equal to 0. And so to do that, I am I'm going to need to do a little bit of algebra now. So I've got this problem, and I have 93.5 minus 78x plus 12x squared equals 0. This looks to me like a quadratic problem. I'm not going to be able to do this by hand, so I'm going to use the quadratic formula. So I'm going to do x equals negative b plus or minus the square root of b squared minus 4a is 12, and c is 93.5. All divided by 2, and a is 12. So now I need to go type all this stuff in and see what I get. 70, let's do minus 4 times 12 times, I don't like having you all here to type these in for me. But at any rate, I've got 78 plus or minus the square root of 1596, all divided by 24. And this is going to give me two answers. And this part right here is 39.94, almost 40. And so one of my answers is 4.91, and my other answer is what I get. So that's the answer when I add them. The other answer is what I get when I subtract them, and that one is 1.585. Okay, 915. Okay, so these are my two answers. So 4.915 and 1.585 are my two results when I put these together. Now the question is, what's the best one? Which one do I need to do? Do I need to cut my sizes at this size or this size? And well, let's come back to our picture, and I think you'll notice a few things if you look at it. So first, we could think about what our equation looks like. But second, we can kind of think about logically about this. This problem right here had a natural domain to talk about. And the domain is what is the largest and smallest that x could possibly be. And so the smallest x could be, domain is, well, x needs to be bigger. Well, it doesn't make sense for x to be a negative number. So we would need x to be greater than 0, because putting negative numbers inside of this equation doesn't make sense anymore, right? Similarly, if we make x too big, all of a sudden we're cutting squares that are over halfway, and so we can't get over halfway. So we need our x to necessarily be less than half of 8.5, and so 8.5 divided by 2 is 4.25. So we need our x to be somewhere between 0 and 4.25. So that tells me right now that this one is going to need to be our answer. So just thinking about our domain, we realize that at 0, we're going to get, so if I were to think about this as a graph, at 0, I'm going to have 0 for a value. And at 4.25, I'm going to have 0 for a value. And what does my graph need to look like? It needs to come up and go down. And so that maximum is the 1.585 value. So that's the maximum that we get when we do this problem. How else could I have thought about this? Well, another way I could have thought about it is I could have thought about it in terms of my function. And so if I think about my function, this is an x cubed function. We all kind of know what x cubes look like, don't we? We know that x cubes always go up and down and up again, and this one goes through 0. And so this x cubed is going to go up, down, and up again. And what you can see is that part of these don't make any sense. Like this part of the graph is nonsense. Why is it nonsense? Well, it's nonsense because you're getting like a negative volume for your square. That's when you're cutting out squares that are too big for your piece of paper. And so if we think about that, where's our maximum value? Our maximum is right here, and you can see these two numbers. This one must have been the maximum, and this one must be that kind of nonsense minimum over here. Okay, so there are a few ways to think about it. What's the last way that we could do it? The last way, if you're having trouble doing this, well, we could just very simply draw ourselves a number line and put these numbers on here and put 1.585 on it and 4.915 on it, and then check each section. And what you would find is that you're increasing, decreasing, and increasing, and so that means that this is a max right here versus this one, which is a minimum. But at any rate, you have to kind of ask yourself, am I allowed to make my squares infinitely large? And the answer is no, that doesn't make sense. You're limited on your squares. Okay, I hope the justification wasn't too confusing, but at some point at the end of the problem, especially when you get two answers, you have to stop and think which answer is the right answer. And it turns out this one must be the right answer because this answer doesn't make any sense. You can't cut out a square of 5 inches when your board is only 8.5 inches long, because then you're going to be cutting out a square that's too big. Okay, well, I hope that made a little bit of sense. Turn over and try the next problem. And we're trying to make a box, or let's see, no. So turn over the next problem, and there's a little bit of trick to it. And so I'm going to do something that's going to make it a lot easier. But do it yourself first before you see what I do.